So once again, just to remind you, today's lecture and Wednesday's lecture will be on the exam on Monday, right? Um, but then the lecture we have on Monday will not be on the exam, okay? Which will be the introduction to thermochemistry and electrochemistry, okay? So like we were talking about last week, not last week, was it last week? It was last week. We were talking about what are the situations in which you have a common ion, right? And the common ion makes it so that practically when you're working these problems, you have, instead of having zero for initial products, you'll have some, something in there for the initial products, which you work them all the same way anyway, right? So for the KPs and for the KCs, you've got to use the quadratic equation. But for weak acids and weak bases, you can just use the drop the minus x method, right? Drop the minus x method. Not dropping x, but dropping the minus x, right? So you still have the x squared, right? You still have to do that, but you can drop the minus x. So when you have a common ion in a solution, right? And what happens is that when you have a common ion in a solution, it does this thing called the common ion effect, right? Which is what we talked about last week, where the common ion effect makes it so that there would be less less solute dissolved, right? It will be less ionizable, right? And so this effect is actually called a buffering effect, okay? And so now we're going to be talking about buffers. And so buffers, right, are solutions of weak conjugate acid base pairs that resist drastic changes in pH. These are called buffers, right? These solutions contain relatively high concentrations, uh, 10 to the minus 3 molar or more of both acid and base, and their concentrations are approximately equal. So what you actually see in this picture here are actually buffer standards. We use these a lot in chemistry. If you ever used a pH meter before, like a pH pen, and you stick it in there, it tells you what the pH is, right? For those things to know what pH is what number is what concentration is what, you have to actually use these things. So usually it's like pH 4, 7, and, oh, sorry, that says 4. 4, 7, and I think that says 10. I can't really read it, but those are normal. And so you stick the pH meter into the buffer solution, and you tell the pH meter, this is what it looks like to be pH 10, right? And then it goes, okay. And then you can do it again for this is what it looks like to be pH 7, and you do it again, this is what it looks like to be pH 4. And so the way that pH meters work is that they are able to tell pH, which is hydronium ion concentration, by the electrical current, right? That's that's conductible inside the solution, right? So that's how it tells. And so these buffers will actually at these certain pHs will give a standard reading for the pH meter to know what the current will be at 4, 7, and 4, 7, and 10, right? And you want to do that because pH range is 0 to 14, right? But you want to use standards that are in the middle, right? You don't want to ever. One thing that you'll learn a lot in analytical chemistry, forensic sciences, all kinds of stuff like that, is that you never want to measure anything at the extreme. Okay. So, for example, if you're using a pipetter that is 1,000 milliliters, or sorry, microliters, you never ever want to go all the way up to 1,000, right? If you're going to do that, you might as well use a 2.5 mil pipetter type of thing, because we find that at the edges, at the extremes, it's very inaccurate, right? And so it's the same way with pH. We don't want to put standards at the edges, right? We want to put them in the middle, because the vast majority of the solutions that we talk about are going to be like this, unless you're going to be why would you put like a pH meter into concentrated sulfuric acid that's going to be less than 0 pH? That would just not make any sense at all. So that's why a lot of people ask, why do we only use 4, 7, and 10? It's because you never want to do a standard that's at the edges of the actual range of what you're reading, right? So how do we make a buffer? How do we make a buffer? We make a buffer, number one, by mixing a weak acid and the salt of its conjugate base, right? The salt of its conjugate base, or a weak base and the salt of its conjugate acid. So the prime example of this, right, we use in biochemistry a lot is phosphate, right? We use phosphate buffers. We call it PBS, right? Phosphate buffers. That actually is PBS saline, so it has the S stands for saline, some salt in it too. But the way we would do it is we'd have phosphoric acid being the acid, right? And then we would have phosphate ion being the conjugate base, and that phosphate ion comes in the form of sodium phosphate, right? Another one that people use a lot too is acetic acid and sodium acetate, because acetic acid has the acetate ion, so the common ion there would be the acetate ion from sodium acetate, right? Those kinds of things, okay? And then you add a strong acid, particularly a strong acid, and particularly neutralize the weak base, or add a strong base to partially neutralize the weak acid. Okay. So when I was telling you that a second ago, I was saying how we use sodium acetate or acetic acid, and then we had phosphate and the phosphoric acid. The phosphoric acid in that case would be the strong acid, right? So it's interesting stuff. How does a buffer actually work? All right, how does a buffer actually work? Well, uh, practically what it does is that it makes it so that there's not huge changes in pH, right? And the one most common, and you carry it around in your bodies all the time, right? And it's the reason why you're alive right now. And it's called the carbonate bicarbonate buffering system in your blood. And I think I've talked about this before, but just to reiterate again, your blood has to be an exact pH of 7.4, okay? If it's any higher than that or any lower than that, you could get really sick, okay? It could kill you, actually. And so the way that your body actually maintains that pH of 7.4, right, is by using what we call the carbonate bicarbonate buffering system, which actually uses carbonic acid, right, and the carbonate or bicarbonate base, conjugate base, right? And it goes back and forth, making sure that your pH is 7.4 in your blood all the time. Um, and so, and if you think about it, if you think about it, if you have a a solution that's 7.4, right, and there was not any buffering action, and you add in, you get, let's say you drank something super acidic, right, like orange juice, for example, right? You know, something that's super acidic like that, right? Or you ingested something that was super acidic, it would immediately change the buffering, change the pH in your system, right? And if it changes too much, you could get sick. So that's why we have a buffering system in our bloodstream. And so in this case, say you drink something acidic, and I'm telling you this is very rudimentary right here. This is not like exactly how it works. But say you consume something acidic like orange juice or lemon juice or something, tomato sauce, that's also very acidic too. Coca-Cola is very acidic. Um, and and then it gets into your bloodstream, and then you have in there the carbonate ion, right, which is the conjugate base, right? It can accept that proton, and when it does that, it makes it so that when the proton's being accepted by the carbonate ion, it doesn't float around free in your blood, and it's when it's free floating around in your blood is when your acidity goes up. Does that make sense? So basically, what a buffer does is that it has free conjugate base is floating around, and it will, and then when you add an acid, right, it will grab those protons from that acid so that it doesn't stay in solution, making your acidity go up. Does that make sense? Right? And the same thing can happen in the other direction too. It can get more basic as well. Okay. And we saw in the previous slide, right, that our previous lecture, that not only does your blood need to be a certain pH, right? Your intestines have to be a certain pH. Your stomach has to be a certain pH, right? It's especially important in your intestine because you have bacteria in your stomach, right, that are actually involved in your digestion. And if it gets too acidic or too basic in your intestine, right, you kill off that bacteria, and then you're really, get some gastrointestinal issues now, right? So let's talk about then how this works chemically, right? So I use carbonate as an example because that's in your blood right now, the carbonate bicarbonate buffering system. But here they're using the fluoride ion as the buffer. Okay, so here's a solution, right? And if you have in here, right, if you have in here hydrogen fluoride, right, some of it will be some of it will be hydrogen fluoride, and some of it will be the fluoride ion, right? Some of it will be the fluoride ion, okay? And the interesting thing, or the thing that's very helpful here, is the fact that when you have like in a buffering system of fluoride and you add some protons, right, which makes things more acidic, you get more hydrogen fluoride, right? It used to be equal right here, right? It used to be HF is equal to the concentration HF is equal to the fluoride ion. But since there's a buffering system in place where we have an excess, not an excess, but like we have fluoride ions almost in the same concentration as HF, you can add more protons and then the hydrogen fluoride concentration goes up, right? And then the fluoride concentration goes down, but it doesn't change the pH because the protons aren't freely floating around, right? If the protons are freely floating around, that's when your pH would go down or your acidity would go up, right? And it happens the same way on the other side too, right? Again, we have here a concentration of hydrogen fluoride, and then we have the fluoride ion, okay? But if you add in some hydroxide, okay, then the hydroxide will pull off the proton from hydrogen fluoride, making water, okay, and then making more fluoride ions, but neither water nor fluoride ions actually increases pH, right? Does that make sense? You have ions in solution that can either occupy protons or occupy hydroxides to maintain the pH in a buffer, okay? It maintains the pH in the buffer, right? So adding a small amount of acid or base will only slightly neutralize one component of the buffer, so the pH doesn't change much. Okay. This is actually a pretty cool slide here, or a pretty cool diagram here. Okay. Pretty cool. So your first question today is this: which of the following is not true about buffers? They are strong solutions. They are solutions of strong conjugate acid-base pair that resist drastic changes in pH. That seems reasonable. They can be made by mixing a weak acid and a salt of its conjugate base, or a weak base and a salt of its conjugate acid. It can be made by adding a strong acid and partially neutralizing the weak base, or adding a strong base and partially neutralizing a weak acid, or dang, my laser died. Or adding a small amount of acid or base only slightly neutralizes one component, so the buffer doesn't change much. Dang it, my thing died. So sad. I wonder if there's a way to charge it real quick. And I got logged out of this thing. Very frustrating getting logged out. There you go. Forms. This one is a tricky one. There's a lot of words there, so I don't blame you. Leave. Let me find this here. Okay. Still waiting for a couple more people. Talk about it if you need to within your group. Okay. Okay, so the vast majority of you got this one correct. Very good job. I wish I could point at it, but I don't have a laser, so I can't. The answer is, in fact, A. It should be a weak conjugate acid-base pair. It should be a strong. Okay, so good job there. This is really inconvenient that I have to use a meter stick now. I'm glad it's here, but it's very inconvenient. Okay, so let's do a little quick review. Right here we have a weak acid, right? For weak acid, we have Ka that equals the hydronium ion concentration or the proton concentration times the conjugate base divided by A, right? So say we need to take the pH, we have to figure out what the pH is of a buffer, right? What you need to do is take the log, the negative log of the Ka, right? And take the negative log of this side as well, right? Take the negative log of that side as well. So you have this now, right? Okay. And then you can rearrange the equation now so that it says the negative log of the hydronium ion concentration, right, equals the negative log of the Ka plus the log of the conjugate acid divided by the regular acid, right? And something should already look familiar to you, and it's this right here. What is that right there? Exactly, that's pH, right? That's pH. So all you need to do is plug in the Ka, plug in the concentration of the conjugate base, plug in the original concentration of the acid, and you get pH, okay? And this is actually a very, very common equation, right? Oh, by the way, does anybody remember what P stands for? I talked about this before. Huh? Huh? Say again? No, no, oh, no, 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 no. P, the letter P, when you put it in front of anything, what does it mean? Say again? You do know. No. Give you a hint. Okay, I'll give you a hint by going backwards. Look, okay? So if pH is the negative log of the hydronium ion or the proton concentration, hydronium ion concentration, right? What does pH mean? What does the P mean? Oh no. I'm getting like really bad signal today for some reason. It's never been like this before. There we go. So if the negative log of the hydronium ion concentration slash proton concentration is the pH, right? What does the P in pH mean? We already know that the H in pH means what? Proton, right? So what does the P part mean? Yes, exactly. When you see the negative log of anything, it really means P, right? It's P, okay? Does that make sense so far? It's just the chemists are like, they're lazy, so they don't want to write out the word negative log. So they just, they say, okay, negative log means P. So that's why it's pH. It's short, right, for negative log. Okay? That's why this is pH. Remember pH equals the negative log of the hydronium ion concentration, right? Does that make sense already yet? Yes? If pH is the negative log of the hydronium ion concentration, right? And the H part of pH is the hydronium ions, then what does the P part mean? Negative log. I mean, it's possible. They are German, actually. Most chemists are German. The early chemists, right? I know it's crazy, but yeah. So if you have the negative log of the hydronium ion concentration or the proton concentration, they mean the same thing, right? This negative log here is just P, okay? People just say P, lowercase p, right? And this part here is the H, right? So you put it together and you get pH. And the reason why you do that is because this number is usually a very difficult number to deal with. It's always a number that's a hydronium, it's always a number that's a scientific notation number, right? And so when you take the negative log of anything, it turns something that's a scientific notation into something that's in between the numbers of 0 and 14 for pH, right? Does that make sense? Okay, so if this is pH, right, negative log of the negative log of the proton concentration or hydronium ion concentration is pH. What do we think we change this to here? The negative log of Ka. Say that again. Who said? Say that again. Yes, pKa. Right. This is pKa then. Okay. So one of the things you'll learn, especially when you go through analytical chemistry, biochemistry, all those other chemistries that you might have to take later on in life, organic chemistry, pKa is actually what we use in chemistry to determine how acidic something is. Okay? So the smaller the pKa, the more acidic it is. The bigger the pKa, right? Sorry, let me say that one more time. The smaller the pKa, yes, that's right. The smaller the pKa, the more acidic it is. The higher the pKa, the more basic it is, right? Or the less acidic it is, okay? And so, for example, now we have this equation, right? I don't know why I said example. So now that we figured that out, we have this equation where pH equals pKa plus the log of the acetate divided by the original acid concentration. And this is an equation that you'll use a lot in life, right? Especially in the next few chemistry years, semesters. It's called the Henderson-Hasselbalch equation, okay? So the only reason why I went through all that was just to show you where that pKa came from, right? It literally just means negative log of the Ka, right? Does that make sense? Do you know why we change it to pKa like that? It's because usually when you see a Ka, isn't another number that's like got a scientific notation in it, right? So chemists want to make it easier by just getting negative log, and then it becomes like a whole number, you know? So you'll see pKa's that are from 0, which are the strongest acids, like sulfuric acid, things like that, all the way to 50. And 50s are very weak acids, they're very strong bases, right? So this is the Henderson-Hasselbalch equation, okay? So if you have a Ka, which oftentimes you have a Ka, because you can look that up on a chart. Remember that, right? Remember that chart I showed you that had a list of all the known Kas? Okay? So if you get a question on an exam that has you might have to figure out what the conjugate acid is, right, from the ice table, but you'll always get the initial concentration, right? And then you have the Ka, right? The Ka from a chart, or it's going to give it to you in the question. Then all you have to do is plug all that stuff in, and you'll get the pH of a buffer, right? The Henderson-Hasselbalch equation is quite useful, okay? Quite useful. So you can see why I don't want to put this onto the I didn't want to put this on the next exam, because you're not going to use it at all in the next exam. It'd be very confusing to have both. So here's an example, okay? Say I have a solution, a buffer, that is 0.1 molar lactic acid, right? And then, which is this formula right here, lactic acid. And then I have 0.10 molar sodium acetate. I'm sorry, sodium lactate, right? And I have a Ka, right? I have a Ka that is 1.4 times 10 to the negative 4, right? What is the pH of the solution, right? What is the pH of the buffer? So it's really simple, right? Because you're usually given a Ka, or you can find it in a chart, okay? And then you're given the acetate concentration, which is 0.1, goes at the top, right? And then you get the initial concentration of the acid, which is 0.12, put it at the bottom, right? And then all you have to do now is go 3.85 plus, this part here is the 3.85 part, right? And then we have minus 0.08, which is a log of this part right here, and then you get a pH of 3.77. No ice table needed, right? No ice table needed, okay? Isn't that cool? No ice table needed. Huh? Anybody have any questions about this example? It's pretty easy. Yeah. Yeah. That is a good question. Yes. Yes. That is a very good question. Okay. HA is always going to be the unionized acid, right? So it will be always be called lactic acid, okay, or some kind of like acetic acid. It will always have the acid in its name, right? And then the conjugate base here, A minus, will always have an 8 at the end because it's an ion, right? It's a negatively charged ion. So it will always have an 8, right? So for the purposes of this particular kind of question, always think that the one that says acid is going to be at the bottom, right? And the one that says 8 will be at the top. Okay? Make sense? Good stuff. Good stuff. Don't worry, we'll get more a little bit deeper into this on Monday, or not Monday, Wednesday. But because class is almost over for right now. But this is what I really wanted to show you before too long, which was this, the Henderson-Hasselbalch equation. Okay, so a couple more slides. Let's get to the next question, and then we'll go over to do discussion. Okay, which is only two more slides. So what is buffering capacity, right? All this here just says this one thing. Most buffering capacity is going to be plus or minus 1 pH unit. Okay, so for example, if you're talking about the carbonate bicarbonate buffering system in your blood, and your blood is pH of 7.4, the buffering capacity of the 7.4 in your blood is plus or minus 1 pH, right? That means it can handle, right, protons and hydroxides up to 6.4 pH or 8.4 pH, right? Plus or minus 1 pH. Does that make sense? That's exactly what that says up there. In a lot of words, it says that. Okay? Buffering range is plus or minus 1 pH, okay, unit. The vast majority of them are like that. Okay? Any questions about that? Is that confusing at all? Okay. So this shows you why. That's a that's a that's a typo. That should be a lowercase p right there, right? But the range of a pH value over which a buffer system works is effectively the optimal pH where the concentration of HA equals the concentration of A minus, right? So if one concentration is 10 times more than the other, the buffering range is 4. This means that the pH range of a buffer is usually what? 1 plus or minus 1 pH units. Does that make sense? Right? All right, so this is the last slide for today. Your last question. And then we can go over to the other room and do our review if you want to. You don't have to come to that. But that doesn't mean that discussion is not required. You are required to go to discussion. Just this time, since I'm the one that's in there and I'm doing a review, you don't have to come to discussion. You don't need to. Did you say you're dying? I'm so sorry. Is this what you said? Am I killing you guys with this stuff? If anything, I gave you an equation that you can use for almost anything now. Mary keeps on telling me I need to put equations on the exam for you guys. I'm trying to figure out what equations those could be. So, that's not even an equation, Mary. You're talking about, oh, the one that said the change in the number of moles is the final number of moles minus the initial number of moles? The what whole thing? Are you talking about P? PV equals nRT. You need me to tell you that? It's fine. It's fine. Okay. Let's see how you guys answered. Before you leave, let's see how you answered. Buffering range. Still missing one answer. Who's not responded yet? Oh my God, someone got this one wrong. Did you do it on purpose?
I thought you said it's plus or minus 4.
Are you serious?
I'm tripping. Did he not just say that?
That's not even an answer.
I understand that, but that's why I'm confused.
Did I say that?
You said plus or minus 1. I'm tripping.
What? Oh my God. Mary, what is wrong? What is going on here? Did I say 4 ever?
I'm tripping.
I don't think I ever said 4. I'm just saying. I don't think I said that. Okay, here we go. Everybody's there. Someone got it wrong. It was Mary because she blew up at us just now about it. So, put your tables back together. Let's head over to the other room. Holy cannoli. Did you really think I said 4? Oh, man.